Hi, my name is Avanzini, and in this short video I give you an overview on our work on continuation passing transformations and expected cost analysis. This is joint work with Gilles, Barthe and Lago. So in this work we are interested in a resource analysis of programs. Such a static resource analysis is a well-established research field where a lot of different techniques have been proposed. However, most of these techniques are confined to sequential models of computation. On the other hand, if we look at application areas such as, for instance, cryptography or robotics, then the underlying model of computation is inherently randomized. This motivates us to look at probabilistic programs in the sense of ordinary programs that have some source of randomness built in, for instance through the use of sampling structures. A computation should then really be conceived as a stochastic process that ends up in a distribution or subdistribution of possible outcomes. Concerning cost or resource analysis, it's very natural to assign a unitary cost to certain primitive operations and then define the cost of a computation simply as the accumulated cost of all the operations that have occurred. Now, in a sequential setting, we would be interested in maybe in finding an upper bound to this cost function. In a probabilistic setting, the cost itself of a computation is a random variable, so morally it depends on the random choices that have been performed in this computation. What we will now be interested in is to find an upper bound to its expectation, so to the mean value of this random variable. To make this a bit more concrete, let's look at an example. In these boxes of cereals, you have 1 out of 6 actual figures. Now you may ask yourself, how expensive is it really to collect all these actual figures? And a good way to reason about this one may be to look at how many boxes of cereals you have to buy on average in order to receive all these 6 actual figures. This is an instance of the so-called coupon collector problem, which is modeled by this small probabilistic program here drawn above. So this function coupons takes a list of all coupons that could, for instance, represent the actual figures 1 to 6, and then simply iterates by collecting new coupons by drawing uniformly at random a new coupon from the list of all coupons and adding it to the collection that we already own. So on the surface, this is an ordinary functional program. However, we consider 2 additional constructs. The first construct is this tick here, which is our way to impose a resource model on such functions. It essentially tells you to consume now 1 resource unit, and we have sampling in structures like this draw procedure here, for instance. Now, if we look at the evaluation of this function, for instance, with coupon number 1 and 2, then we could be very lucky and after 2 iterations, so with cost 2, collect all the 2 coupons, or we could be unlucky and never finish collecting coupons. However, on average, the number of draws that we are performing can be shown to be bounded by this expression here. Okay, so if we come back to the example of cereal boxes, n is the number of coupons. If we substitute 6 here, then we see that on average 14.7 cereal boxes have to be bought in order to collect all these coupons. And the question we are asking now is, how can we formally derive such bounds? There has been actually a lot of research going on into this direction, but most of the works are confined to imperative probabilistic programs. Just recently, we see some novel techniques, among them also work by us, that makes use of type systems to reason about the expected resource usage of functional programs. The problem with this approach is that it's very difficult within a type system to capture probabilistic effects at the same time in a concise and precise way. The implication of this one is that when you design such a type system, you will have to make a trade-off between the expressiveness of the type system and the way how difficult it is to reason within this type system. Now, another approach generally to resource analysis goes back to the work of Wegbreit of 1975 that makes use of program transformations. So in his work, Wegbreit considers functional programs and extracts from these functional programs in a systematic way a cost function. Now this cost function itself is again expressed as a functional program, which allows us now to use conventional tools for program correctness to also reason about the resource usage of programs. The approach that we are proposing for probabilistic programs falls precisely within this framework. We start from a higher order functional programming language endowed with sampling operations from discrete distributions and these cost annotations through ticks that we have seen for an example. And on this we apply our expected cost transformer that extracts from this program in a systematic way an expected cost function. And crucially, this expected cost function is represented now as a non-probabilistic program. This means now, again, we can use conventional tools from static analysis to analyze the image of this transformation in order to reason about the expected cost of our probabilistic programs. So this picture sums up our two main contributions. On the one hand, this cost transformer, and on the other hand, an adaptation of a higher order logic to reason about such cost functions. Now this expected cost transformer is actually inspired by the expected runtime transformer of Kaminsky and others, defined in 2016, that gives a sound and complete methodology for reason about the runtime of imperative programs. The idea is that this cost transformer transforms to a cost of a continuation to an overall cost. So it will yield a positive real number or infinity in case the overall computation has an unbounded cost. Now what we realized is that on the pure fragment, this cost transformer is simply an instance of the one-pass continuation passing style transformation that you find, for instance, in the literature by Danby and Nielsen, which gives the name also to our paper. The crucial aspect of formalizing this transformer in a continuation passing style is that we now can extend this notion very seamlessly also to our impure fragment of the language. Whenever we see a tick term, we just add 1 to its expected cost, and whenever we see a sampling instruction, morally what we are doing is we simply compute the expectation, so the mean value of the cost of this continuation kappa with respect to the sampling operation that we are performing. Possibly also first evaluating the arguments m to this sampling instruction. To make this a bit more precise, if we, for instance, transform cost of a continuation kappa with respect to a unbiased coin flip that is tick, then this amounts to 1, accounting for the tick, plus kappa applied to head and tail respectively, both of these probabilistic choices weighted by the corresponding probability 1/2. So on our coupons example, this transformation results in this function here depicted to the right. It's structurally identical to the original function, just in addition it takes a cost of a continuation k as argument, and the tick and the probabilistic sampling structures are resolved correspondingly. Now the cost of this coupon function itself we can now express in terms of this CPS version, where we instantiate the cost of the continuation as the constant zero function. Now, of course, because these two programs are structurally similar, and the first program is potentially non-terminating, so is also this cost function defined as we have done so here. So this cost function evaluates to such an infinite tree, and what we can show is that the cost defined in this way converges precisely to the expected cost of the initial program. So far so good. We have now a functional representation of the expected cost of our probabilistic programs, and what we would like now to do is to find a closed expression for the so-defined cost function. And to this end, we make use of an adaptation of the higher order logic. So this higher order logic that we are introducing is a formal system for deriving judgments of this form. Morally, they are annotations of an ordinary type judgment with assumptions on the environment and a conclusion on the result of evaluating such a term. In addition to our type system, and this again is a crucial aspect, it allows us to reason about the converging behavior of non-terminating functions. As a small example, consider this recursively defined function. It's defined so that it converges to this infinite sum here. And crucially, in our system, we can reason about such converging functions in an inductive way, where we can use the conclusion of our judgment also as an inductive hypothesis, morally. Of course, for this to work out, we have to put some restrictions, and the restrictions that we are putting is that we allow only certain predicates for reasoning about such terms, precisely the so-called admissible predicates. In particular, this enforces some notion of continuity, so that we can reason about the limit of a continuation on these predicates. The practical implication is that we can reason about upper, but for instance not at lower bounds of such functions. Okay? So what you have seen in this short talk is how we use a CPS transformation to turn the cost of a probabilistic program into an extensional property of the pure program, which enables an average cost analysis through more or less conventional static analysis tools. This encompasses the aforementioned ERT calculus of Kaminsky, but is also capable of reasoning about higher order functions. As a side note, using this methodology, we can also reason about pre-expectations. Concerning future works, we really would like to have our system integrated into a proof assistant with partial automation. We would like to also be able to reason about lower bounds and non-monotone costs, which are currently outside our framework. Thank you very much for your attention, and I'm happy to answer your questions.